going to happen. I'm very briefly going to finish up a few things on model selection. Okay? Then I have a whole set of slides that, shoot, I didn't during the faculty meeting export and send to the GitHub repo, so I better do that right now. Faculty meeting got kind of hot and bothered, so I got distracted and didn't do what I meant to do. Okay, that's up now. Sorry about that. Okay, so I was starting with model selection finishing. Okay. So high score style stuff is bad, but it's statistically bad in the sense that all these benchmarks, right, like this ImageNet thing, there's a defined test validation and training setup for ImageNet, okay? Everybody who's turning in a high score on ImageNet, they're turning in a high score based on the same training validation test scheme, okay? So is it possible that the high score on the test set is overfit to the test set? Yeah, because everybody's using the same test set. So the winner on the test set, that could be by chance, right? And if you gave it another 2 million photos that come from the same distribution as original ImageNet, there might be some variability in performance on that test set. So high score is a crappy way to do stuff. But it is what you will see out there in the current deep learning environment. Again, why is that? It's because it's really expensive computationally to run these big deep learning networks. It's because it's really expensive, even more expensive than running them or training them. It's more expensive even that to create new data. Creating a bunch of perfect little images with exactly the right size on brand new topics that don't already exist, that requires paying some undergraduates to go do this stuff, right? It requires, like even worse, is getting good text data. We've already used all of Wikipedia and all of Reddit. Where else are we going to get cheap text data, right? So these things, creating new test data sets, creating new model runs to validate, they're expensive. So people go to this high score kind of thing. So in general, if you're not doing deep learning, if you're not doing internet-sized data, right? If you're doing something which is like for a company and you've got like all the sales data for however many years, hopefully you have enough data to have enough folds to do something a little bit more statistically, what's the right word? Proper, right? Proper statistical testing. So you can, given a bunch of folds of cross-validation, test whether algorithm A is better than algorithm B using your favorite statistical hypothesis testing framework. There are a bunch of them that have been very, very specifically rolled out for this kind of work over the last 25 years. I don't have the time to cover that kind of stuff in this class. But if you would like to see a lot more about the framework for doing classic statistical inference like t-tests and f-tests on machine learning stuff, you should read that white paper by Rashka that I linked to in the beginning of this section. Okay? It's on the slides. That white paper covers a pretty good smattering of those kinds of inference tasks. Okay. I didn't say this much in COGS 108. I'm starting to say it now, but you all didn't have me then. Just a reminder that any statistical inference, what you're doing is you're reporting a p-value. What's that p-value? That p-value is the likelihood of, given that there's a null situation, that there's no difference between algorithm A and algorithm B. That's the null, no difference. What's the probability of observing test scores for A and B this far apart, or even further apart, right? This weird or weirder given a null, given that there truly is no difference between algorithm A and algorithm B. You have now, in this class, seen enough Bayes rule, and you should have had enough stats to know the Bayes rule before, to understand that the p-value is the probability of the data given the null. P-values are this. But we use them like they're this. All, t-test, ANOVA, everything, everybody who does inference with statistics using null hypothesis testing, they act like what is this is actually the probability of the null itself. It is not, as we know from Bayes' rule. So, very, very commonly, any p-value, as you can see, gets corrected by other factors. And if you calculate a p-value, a possibility of a false positive result, that's what a p-value is, probability of getting something this weird or weirder when there's truly no difference. So these p-values, if it's like 0.001, seems like a great p-value, right? It's way under 0.05, that magic number. Everybody's like, 0.001, this is really different, right? No, because this normalization will very typically change this number for the worse. Okay? So if you read, you can go out and find the American Statistical Society, I can't remember what the acronym is, has a really great white paper, like a 3-page white paper about how not to be wrong with p-values. You should definitely go find that and read that. Okay. So I oftentimes advocate for the exploratory data analysis approach. Why bother with hypothesis testing when A, it's wrong, B, even when you do it right, it still is wrong, right? So at least showing that there is a clear difference between some approach and some other approach on a data set can be useful. How do we do that? Very typically, we somehow show the variability of results for different categories of options, right? Like a box plot, which shows you that if we have a bunch of cross-validation folds, in this case, I just made up a number, right? So if there's 15 folds, if there's this 3x repeated 5-fold cross-validation, remember that? If we do 5-fold cross-validation and we reshuffle the data and do 5-fold cross-validation 3 times, that means that we have 15 estimates of model performance for every model that we check. And if you look at, say, like a box plot or some other plot that shows you what's the central tendency and also what's the spread, you can see that, hey, you know, it really does look like this might be a lower metric than these. But these are maybe all pretty much the same, even though like a mean or a median value pulled out of the middle there might actually look different on a high score chart, right? A high score chart would just report the mean value of these distributions.
Wait, so are you suggesting that in some cases you just eyeball it?
Well, EDA, like exploratory data analysis style stuff, what it's looking for is it's looking for results that are so crystal clear that you can eyeball them, right? Whereas with a p-value, two things are wrong with that. Well, three. Number one thing that everybody knows is don't just say that stuff less than 0.05 is actually important and stuff that's 0.06 and higher is not, because that's not true, right? That may make more sense to you before you even, get to anything machine learning stuff. Number two is that p-value is not the probability that the null hypothesis is correct. That's the Bayes rule thing I just went through. Number three is that you can make anything significant with a big enough n, right? A difference this big is statistically significant if you have enough n to show that it is. So this kind of an approach looks for two things. It looks for things that jump off the page like that. And if it jumps off the page, if it's visible as a pattern under this kind of a circumstance, that also means that the effect size is not this big. The effect size is large enough to observe, and therefore large enough to care about, right? It is still EDA. This is a line of evidence. It is not truth. The statistical hypothesis framework exists because it quantifies the level of confidence. This is not quantified. But it's still good enough, and it's still better than high score reporting. Right? Because high score reporting would just be take that median line or the mean line that's in these box plots and report that. Does that make sense-ish? People are still thinking. I see that. Okay. So let me introduce the idea of, given a quantified version of not just a central tendency like a mean or a median, but also a spread like standard deviation or interquartile range in the case of a box plot. Just a reminder, a box plot is a non-parametric thing, and it reports medians and interquartile range, whereas something like this is a parametric or normal assumption, and it reports medians and standard errors, right? So if we have, like this case, one algorithm with one hyperparameter, this hyperparameter is one of these regularization constants, okay? So we're seeing like strong regularization over here and weak regularization over here. And if this is accuracy score on the y-axis, you're seeing over multiple folds of a cross-validation what's the average accuracy and what's the standard error of accuracy among those folds. Okay? Just like the box plot, but the box plot is a non-parametric way of doing this. Doesn't assume normal distribution, and this one does. Either way, they're both ways of showing you what is a mean or central tendency and what is the variability of that, okay? All right, so I actually stole this slide from support vector machines with radial basis functions. You guys don't even know what that is yet. Sorry. But what you can see is that, and I actually said it, I think, I said it backwards. So this is strong regularization, where the final division line is basically a line. And then large numbers are weak regularization, where it fits a much more complicated decision boundary. Okay. So which one's best? One principle you can use is you can say, well, given multiple models that are indistinguishable from each other, prefer the simplest model. Okay? Why would we choose the simpler model given a bunch of models that are all just as good as each other?
It reduces the chance of overfitting.
Yes. Complex models can overfit. Overfit models tend to do bad next year when we get new data, right? What was that?
Would it also be fair to say that, like, kind of piggybacking off of that, because these are very related, it's also to increase generalizability in, like, the long term?
Exactly. It's to increase the generalizability in the long term when we see more data from this process. Okay? So this is accuracy score, so we want a high value. All of these are within a standard error of each other. Right? That means it's hard to distinguish their means. Even though this one right here is nominally the actual highest mean, our parsimony principle would tend to have us picking this one, which is more regularized and therefore the simple model. Okay? This one, no, because it's clearly worse because those error bars are non-overlapping with this one, right? This one is clearly a worse performer. We're getting down into this kind of category, right? So, my argument to you is that when you have enough folds of cross-validation to form a distribution of performances, you would do better to make your judgments on your favorite model based on an EDA-style approach combined with the parsimony principle. Examine the distribution, whether it's parametric or non-parametric, right? We can pretty well see that this one is not doing so well, right? This one's doing better. But do we want this high score, or is one of these more regularized, more simple, less complex? And so even though this one's not the high score, maybe we're going to pick it, or maybe this one, right? Even though it's not the high score, it's just as good because the error bars, or in this case, the interquartile ranges, overlap. But it's the simpler model. Okay? So, high scores, what people often report. I argue to you this kind of approach is more reliable for generalization. Okay, the last thing I want to say is just that there is this whole world out there where people do really abstruse math, proving stuff about what machine learning systems can actually learn and what they can't, and putting bounds on how many data points we need to learn functions of a given level of complexity. This is something that we used to introduce in this class, but I left it out in the last couple of years because A, it's pretty hard math, B, it's increasingly irrelevant in the modern machine learning world, but it does have a few nuggets of wisdom. And the most famous one is Walpert's no free lunch theorems. So the idea is this. There is not one ring to rule them all, one ring to bind them, or whatever. I can't remember the damn thing, right? There's not one ring. There's not one algorithm which is best. There are algorithms which are generically okay at a lot of different problems. There are algorithms which are great at one problem and terrible at others. There is no algorithm which is, on average, the best choice. So you have to look. if you're in a place where there does exist some highly specialized algorithm which is head and shoulders above everybody else, okay, makes sense to pick it. But what may also make sense is, I don't know if I'm in this case. I don't have enough computation time or resources to go looking for this highly specialized winner. So I'm going to pick an algorithm which does generically pretty well. Those kinds of rules of thumb sort of algorithms that people know pretty much do a decent job right out of the box for almost every problem, they exist. We're going to start talking about them in the second half of class. Some of my favorite ones are ensemble-based algorithms, things like random forests and gradient boosting. Okay? They're known really good on average across many kinds of problems, but they're definitely not the best. Okay, so that's all I had about model selection. Does anybody have any questions on that? Yeah.
This is going back to something you were mentioning when we were talking about which model to take. We were talking about the parsimony.
Yeah.
So I understand that picking the simplest model makes generalization a lot easier, and you reduce your overfitting. Is it not also possible to be at risk of severely underfitting your data if you start using that as a rule of thumb of I'm just looking for
So, assuming your training or validation set that you're using to pick this is a good representative sample, I don't think it's a high risk, right? If your sample is terrible for what you want to generalize to, yeah, I think you could. Okay. Because I knocked 20 minutes off the front of this class for this cleanup, I want to start with your questions, okay? If there is something in this review of this first 5 weeks that you want to jump onto, I want to hear it now. Yeah?
Can you talk about how adding a bias term changes up the direction of decision boundaries?
Yes, we can. We can talk about bias terms and decision boundaries. I put it in here somewhere. I feel that I put it in here somewhere. Please be in here somewhere. There it is. Okay. Oh, great. It's an animated slide. Super. Okay. So here's our generic decision boundary. Remember, number one thing, without a b, without a constant term, this baby has to go through the origin. Okay? Why is that? Because there's got to be a point at which the y value being just wx, right? What happens when x equals 0? Can't multiply anything by 0 and get anything that's not 0. Okay? So that's why we need a constant term for 0x to have a non-zero y. Pretty simple math. But sometimes just saying that to yourself makes it really obvious. Okay, so to have a decision boundary that does not go through the origin, that is not y equal to 0 when x is equal to 0, we need to have a constant term bias. Let's think about the nature of the decision boundary itself. So here at this point, x is 0. So wx has to be 0. Okay? But the b term moves us off that y-intercept, 0, and it moves us so that the entire distance in here is going to be b. Okay? So again, this weight vector, the weight vector still sitting at the origin. Okay? By definition, vectors come from the origin. But b is the distance we shift away from that origin in a perpendicular, so in the same direction or anti-direction to the weight vector. Perpendicular, that is, to the decision boundary. Right? So, again, Wx is the projection of the distance the data point is away from that origin. Right? That's Wx plus b. That's the distance you are away from the decision boundary. That's why positive b shifts the decision boundary opposite the direction of the weight vector. There's a hand.
Is W transpose X assuming that W is a normalized unit vector?
It doesn't assume that it's normalized.
Unit vector.
But because W transpose X is the same thing as a dot product, right? It's the same thing as a dot product. That there's no assumption of normalization, but it is the projection of X onto W. So if the weight vector is normalized, then that's projection onto a normalized version of the weight vector. If it's unnormalized, it's a projection onto the unnormalized weight vector. Right? So just imagine that W is a really big vector, big coefficients, right? The projection onto that is going to hit the weight vector like here when it's still like going, okay? But if it's a normalized vector, if it's a tiny thing, then it's going to be several times the distance of the weight vector. So the Wx term, either way, it turns out to be the same distance because it's just different in terms of what it's against, what it's projected onto. It's just linear algebra, I know. But the important part, what you were really after, is that positive b shifts the decision boundary in the opposite direction of the weight vector. Negative b sucks it up and moves it above the origin in the direction of the weight vector. Good? Okay. So, what else? There was another hand. You had a different question. Rock-awk. Rock-awk is very confusing, I agree. Here we go. I don't have the animated graph here. Okay, we'll work with this one. So remember, what the receiver operating characteristics are is let's change the decision threshold. At least that's the easy interpretation of it in my mind. It's the easiest way to understand it. So if you have a decision threshold, p equal to 0.05, bigger than that, I'm positive class. P less, I didn't mean 0.05, sorry, I'm still got statistical testing on my brain. P greater than 1/2, I'm positive class. P less than 1/2, I'm in negative class. But if I want to change my relative rate of true positives to false positives, right? If I want to make sure I don't miss any cancer patients, I can lower my threshold. When I lower my threshold, my probability of classifying somebody who is healthy as cancerous is going to go up. But at the same time, my probability of missing any cancer patient is going to go down. I am trading more false negatives for fewer false positives. Okay? So as I make that trade, that's how I'm moving back and forth on this curve. As the threshold sends me to very few false positives, but a heck of a lot of false negatives. That's where I'm down here. And as I get very few false negatives, but a lot of false positives, I'm heading up to this territory. And a good algorithm is going to maintain very, very few false negatives even as false positive problems go away until some point where it just falls off a cliff. And that is a very good algorithm. And a very bad algorithm, it's a linear trade-off, right? And it would be a linear trade-off if you were just making decisions randomly and you were just changing that threshold on a random number generator, right? Yeah.
Up to what lecture does the midterm go to?
It goes up to everything that we've covered. I'm not stopping with this midterm.
Sorry, I'm a little confused on the y-axis and x-axis.
Mm-hmm.
So we have our x-axis model rate for false positive.
So this is true positive, this is false positive rate. Inherent to this discussion is that true positive rate is 1 minus false negative rate. Yeah.
It says in the midterm review slides there's going to be like 10-ish math questions.
Yep.
What math exactly do you know?
Well, in the math we've covered, like I would understand dot products and various linear algebra things. I would understand the decision boundary question, right? I would understand how to calculate various metrics and vector norms, right? Every time we've touched on a math topic, it is fair game. If what you're looking for in this review is for me to tell you what those 10 questions are going to be on, I'm not gonna. Yeah.
On the subject of math problems, for questions like information gain and entropy, where we have logs, are we expected to keep those kind of contained, like how normally sometimes you leave it as a fraction, like this is what the formula will be?
Yeah, that's a really good question.
So should be
So when we solve problems, if I ask you to solve, for instance, an entropy problem, I'm going to be more concerned with the answer being right, first off, and I don't care if it's in fractional form or decimal form. Nobody is allowed to use an electronic device during the test. So you can be damn sure that I'm not going to ask you something that requires you to do like a 7 decimal place calculation, okay? So fractional form or whole, largely speaking, is probably going to make more sense if I ask that kind of a question. Also, if you make a calculation error, but your methods are good, you're going to get partial points on the math stuff. So show your work. Yeah? Say it louder, please.
You have to derive a gradient in matrix form, like a homework.
Oh, like derive the gradient? Like you may be asked for an analytic gradient or something like that? That's entirely possible. Yes. Yeah, I mean, if we ask for something in matrix form, yes, that is, you've been asked, again, like if you've been asked questions about it in an assignment, it is fair game on the midterm. Yeah? Yeah, that's a great question. The bias-variance trade-off is a very confusing thing. We've talked about it at least twice, maybe 3 times in different circumstances. Okay, this is one of my favorite slides for showing how this works. This is like the most intuitive view of the trade-off. So simple models like fit align, they have a lot of bias. They see the world in one way. Okay? You can give it scatter plots that have got sinusoids, or it's actually generated by a 10th order model. But if you throw a line at it, it's just going to interpret the data as a line. This is a biased algorithm. It's biased to see the world in a fixed way. Now, if you are generating those scatter dots with a 10th order polynomial, and you tweak the parameters just a little bit on one of those x to the cube or x to the 8th terms, you're going to get some fairly radically different lines, right? And that's also true if you give it data and you let it fit a 9th order polynomial on that data, and just like a slightly different version of this data, like if you replace this one blue dot with this one yellow dot, is going to change a bunch of parameters in the fitted 9th order model. Okay? But if you change from this blue dot to this yellow dot in the line version, the overall slope is hardly going to change. The overall intercept is not going to change very much, right? This has got great resistance to variability because the simplicity of the model forces it to reject a lot of the nature of the change, right? That's the bias-variance trade-off in its most pure, easy-to-understand form. Simple models just aren't affected by noise as badly as complex models. A complex model will tend to change parameters dramatically for a little bit of noise change. Okay. And so, yeah, sorry. Go ahead. Is it a totally different question, or are you following on? Okay. All right, so just to finish off the idea of the bias-variance trade-off, you can derive it mathematically. I don't remember, did I even throw that slide up? The mathematical derivation of the bias-variance trade-off? Maybe I have it hidden in a later thing. I do have that slide. Just if you really want to understand the bias-variance trade-off, I do think that understanding how it falls out directly from the axioms of statistical estimation, from the idea that if you have a true relationship plus random noise you can't control, the math of that situation, what you're trying to do is you're trying to estimate the true relationship and reject that noise. That's the basic of statistical inference. And that itself is the origin of the bias-variance trade-off. And every time you estimate anything statistically, you're in the realm of the bias-variance trade-off. Okay, so you want to follow up? Oh, what's it specifically? So when you try to estimate the mean of something, for instance, you can take that f of x, you get this measurement that has a true part of it, the f of x part, plus an epsilon. And what you're trying to do is you're trying to take that and estimate the truth underlying from a random draw. And so it's this kind of math where you're looking for the expected value of the parameters, the expected value of the w's given the data, and you break up those two terms and do a bunch of statistical algebra, and you end up showing that the total amount of estimation error has 3 components. Stuff you can't change, irreducible error, a bias term, and a variance squared term. And so because the total error can't change and the irreducible error can't change, that means that any changes in the estimation are a trade-off between the bias and the variance squared. So.
For the Aerometrics, so you have the true positive ray and its
Yeah.
other names. True negative ray, false positive ray. Is there anything else?
So if you look at the, so we're really going to be I should be kind here. I'm not going to tell you everything on the that confusion matrix is fair game. Let's be honest. We're going to ask questions about true positive, true negative, false negative, right? We're going to ask questions about precision, recall, specificity, selectivity. Those ones that we covered, I'm going to ask questions about. I'm not going to ask you questions about positive predictive value, okay? Right? Like things that are on that matrix on the Wikipedia page that we didn't discuss, not going to ask you anything about those, okay?
The bias variance I was wanting to ask was the one that's with a K-fold.
Okay. Yep. That's another version of this. Great. Okay. Hey, escape key is kind of starting to break down on my computer. Okay. So let's understand this. Because the bias variance trade-off here is flipped depending upon whether you look at the training or the test or the validation, however you want to call it, right? The holdout. So when you look at the training parts, having a big K gets you less variability. Why is that? Because in a 20-fold situation, you're using 19/20ths of the data to train with, right? 19/20ths of the data is training data. So every single split is very similar. There's no variability here because the data is mostly the same. When you do 4-fold, well, then a quarter of the data is gone. 3/4 of it is there for you. There's less similarity from split to split in the training. So the fits are going to be more variable, right? Think about this in the extreme. Think about it if it was just repeated train tests. So a 2-fold situation. How only half the data is available for you for training? So when you're on the other half of the data, stuff could be really wonky on those 2 fits. You might get radically different fits. Okay? So this is all about how much of the data is in the training set. Because almost all the data is in the training set in a high K value for a K-fold, there is very little variance. Implicitly, because there's little variance, there's got to be a high bias. What's the bias towards? The bias is towards the training set itself. Remember, all training sets are random draws. All random draws have noise. So we're highly biased towards the random noise present in our entire training set. Does that make sense? Okay. The picture flips when we go look at the holdout set error, because the size of the relevant set of data flips here too. In the 20-fold setup, we only have 1/20th of the data in our holdout set. So our estimate of error is only based on a tiny fraction of the data. Potentially, our variance is really high here, right? Because only 1/20th of the data, maybe you just randomly draw on this particular split some really wacko data points. And so your error is really extreme, right? It's because if there's a lot of data in training, there's not much in the holdout. And that's why the picture flips here. And what had been the high bias, low variance is now the high variance, low bias. Does that make sense? Yeah, you're like, help me. Okay, yeah.
When there's high bias for the 4-fold set, what is it biased towards when you're doing?
That's a great question. What is it biased towards? So it is, once again, biased towards the noisy nature of the training data, right? So you're estimating. So remind yourself why we're even doing this, right? The idea is by messing with our overall, what we're putting into training, what we're holding out for validation, we're resampling, right? The idea is by doing this resampling, we're trying to get better estimates. We can't really go out and spend the money and the time to get new data sets. So we want to use the data we got and scramble it in ways that make it look like a new data set, right? And that's what resampling is fundamentally about, is scrambling the data we got to make it look like a new training set, to make it look like a new test set or a new validation set. So when we have situations on either the holdout or the training where we're approaching a big chunk of the actual training set, we're not getting a good scramble, right? We're just mostly seeing the training set again and its particular noise. So that's why we can see that with the 20-fold validation curve, it looks radically different than the smaller fold validation curves. Because the 20-fold has such high variability on the holdout, that variability is potentially swamping the estimate. Okay? And especially for very complex models, apparently it's swamping the estimate. Because you wouldn't expect there to be an inherent... The validation is not changing the nature of the model, right? Okay, so
when you're looking to kind of, because this is one of the things on the example I was getting a little
Yeah.
confused about, which was this exact graph. When you care about your model accurately predicting Aerometrics for so again the concept of generalizability, you really want to focus on the you want to have in this context, you want to have the set you're looking at have the noise of what a training set is, right?
yeah.
You want to have so that it's easier to see what it's like. You have more data that you're looking at with the noise of that data size, and you bring the new one, it's more.
You want the resampling procedure to change the data enough that you're getting these fake data sets that are looking different enough, both on the training side and on the holdout side. Yeah, especially in sizes like this. Yeah.
In our math question, can we get away with leaving our answers unsimplified?
Yes, mostly yes. Yeah.
So like if we say for a logit function, like the probability that this is positive is 1 over 1 plus b to the...
I would be fine with that in a test situation. Yeah.
Because we have like a lot of different notation for vectors and now they're
Yeah.
Is there like some standard form that you know is preferred so that they're
I don't care as long as it's clear, right?
arrow
Yeah, if you want to use arrow, I mean, I know it's hard to do boldface with a pen or a pencil. Okay, yeah.
I had a question about the decision boundary and the bias.
Yeah.
If we were to, in the picture that you showed us, if we were to switch the positive and negative class, would it still move in the same direction? Like if we had like W transpose X plus B, and it's like that would move downwards, would it still move down to the positive class?
No, so remember, the positive class is always the side the weight vector points to. That's a definitional thing. Okay? Let me, before everybody runs away, and before we get the next question, I do want to note to people these important things. Many of you have already looked. Just bring a pen or a pencil. Don't show up without one. Okay? The fact that the questions are going to have a bubble sheet that's going to be scanned, you got to mark that bubble sheet nice enough. Okay? It's not perfect. It's actually much better than Scantron, but just mark it clearly. Your written responses, your math responses will be hand graded. You may bring a cheat sheet. Okay? I highly recommend that you hand write that cheat sheet because I think you're going to learn better. But I'm not going to enforce that because I almost got in trouble with that last quarter. If you are mildly ill, like I feel a headache or my stomach hurts, you may come to take the class, the exam in person, but please wear a mask. If you are feverish, and especially if you are coughing, do not come, but you must send me a message before the exam starts that you're not coming. okay? We will make alternate arrangements for somebody that is sick. Please don't use this as an excuse, okay? But if you're ill in the fever and coughing, do not come. If you're mildly ill, come, but wear a mask. I will have masks for you. So yeah, bring your ID too, because on your way out, we'll check your ID. Okay? Any other questions you want to ask in 30 seconds? Okay. Good luck.
Kind of related to something, kind of related to the previous question you had. So where you had you had degrees on the x-axis and degrees on the x-axis, r squared on the y.
Yeah.
My question is, so with the assignment we're looking at, what type of parameters you would expect to best fit your data, but I don't particularly care about that. I'm more concerned with this one where you had the folds. Which, like, would it be better to have like 10 folds as compared to 20? Because I saw as you got further down in complexity, by the time you got to like 10 degrees,
Yeah.
it dipped into like the RT was like 0.2.
Yeah.
So it was very low, and I'm a little bit confused on which one. Like, at what point is what amount of folds better almost?
So rule of thumb is this. Stick around the 5-fold to 10-fold range. Why? Because at like very low numbers of folds, we know we have enough bias that we may not be getting a good estimate, right? Think about where that bias comes from. That bias comes from the fact that we have this, we're approaching a good chunk of the training set, right? So we're biased towards the noise in the training set, and we're maybe over confident about this value. But on the other hand, we know that